Just to tell a few words, very simple, concerning this title and this communication to the Academy of Science, which is also a lecture of the Pedro Nunes Lecture. That was an initiative created by the Centro International of Mathematics, together with the Portuguese Mathematical Society in 2009, with support of Calcul School Banking Foundation. In fact, today we have here, which is a joint event, a session of the Academy of Science of Lisbon, and also a Pedro Nunes Lecture. And the title is here, Taking Mathematics to Heart.
It is a great pleasure and honor to present Professor Alfio Quarteroni to the members of our Academy. Let me start by telling some words about the outstanding mathematical career of our guest of honor. Eu vou fazer uns cortezinhos para não vos fazer perder muito tempo. Professor Alfio Quarteroni is recognized as being one of the main world leaders in various branches on numerical analysis and related subjects, and on its applications to real-life problems. His research interests concern mathematical modeling, numerical analysis, scientific computing, and application to fluid mechanics, to geophysics, to medicine, and to improvement of sports performance. His research group at EPFL, École Polytechnique Fédérale de Lausanne, has contributed to the preliminary design of Solar Impulse, the Swiss long-range experimental solar-powered aircraft project. His research group at the EPFL has carried out the mathematical simulation for the optimization of performance of the Allinge yacht, the winner of two editions, 2003 and 2007, of the famous America's Cup. As you know, the America's Cup is the more important yacht competition in the world, each 4 times. They win 2 times because of design, of mathematical design also, of the group of EPFL, of Alfio Quarteroni. This is the kind history that happens, I will talk about it. About this last outstanding achievement, I cannot avoid describing a fact that strongly impressed me. Professor Quarteroni told me the following. When he and his research group tried to improve the structure of the yacht winner of the 2003 Cup, they arrived to a new, very promising design of the keel. The keel a quilla. Really is not the keel, it's the bulbous. The keel has something, this is the bulbous. The weight of the bulbous is 450 of the weight of all the yacht. Say the yacht is say 25 tons, the bulbous is 20 tons. It's a very important piece. And they, however, they arrived to a new, very promising design of the keel, a new keel. However, after some time, they realized that some features were not completely convincing, so they turned back, at least partially, to more or less the old keel. During the 2007 presentation of the new yacht competitors, when the different racers were finally shown to the public, Alfio realized that the main antagonist yacht has followed the above keel's improvement. The main antagonist has do the following kind of keel's improvement, but they do not do the reverse. They didn't understand that the new thing was not so good. And Alfio told me that in that moment, when he saw the new competitor, he said he understands that Allinge 2 would certainly be the winner of 2007 Cup. And it happens. I think this is very interesting. Alfio Quarteroni is presently Professor of Numerical Analysis and Director of MOX at Politecnico di Milano. Formerly, he was Director of the Chair of Modeling and Scientific Computing at the EPFL, the École de Lausanne. He's a co-founder and president of MOXoff. It's a very important spin-off company at Politecnico di Milan. Professor Quarteroni is author of 25 books, editor of 9 books, author of more than 300 papers published in international scientific journals and conference proceedings, member of the editorial board of 25 international journals, and editor-in-chief of 2 book series of Springer, which is one of the main publishers of mathematical texts. He has been invited to or plenary speaker in more than 300 international conferences and academic departments. In particular, he has been invited speaker at the International Congress of Mathematicians in 2002 in Beijing, and plenary speaker in the International Congress of Mathematicians in 2006 in Madrid. I say that the people not mathematicians, that the International Congress of Mathematics is more important meeting of mathematics in the world, and happens only each 4 years. Has been 2 times the main speaker. Among a long list of awards and honors, I may recall the NASA Group Achievement Award in 1922 for the pioneering work on computational fluid dynamics, and the International Galileo Galilei Prize for Science in 2015, but he has lots of many other different awards. He was also recipient of many important international grants, which I will not enumerate here, otherwise we need a lot of time here. He is Doctor Honoris Causa in Naval Engineering from University of Trieste in Italy, first row fellow of CIAM, the Society for Industrial and Applied Mathematics, EACM fellow, this is the International Association of Computational Mechanics. He's member of the Italian Academy of Science, Accademia dei Lincei. To Galileo Galilei was maybe one of the first academicians, the European Academy of Science, and of the Accademia Europea. Let me say something more outside the mathematical career. I think that the presentation of scientists should not hide some words about the man. Alfio Quarteroni is a very open-minded personality, always helpful and indulgent to anyone. He clearly knows his outstanding value as a scientist. This is not in contradiction. I will say it is even in agreement with his kind and modest attitude in life. It could be unusual, but not superfluous maybe, to take this occasion, because it's maybe the unique occasion, to let know to our academicians that Professor Quarteroni, something about family of Alfio Quarteroni. Wife Fulvia is a medical doctor. They have 2 daughters. Silvia has a PhD in computer science. Marzia, a master in economics. They are really very high level they are top level in both of these things. And I also, Silvia has a baby Lara. This also Silvia. I am just Another thing I must say to end is a delicate point, but I will say, talk about that. Where is Alfio? He's not here.
It's here.
Ah, see.
Behind you.
I look for you. I cannot avoid to say that the first part of Professor Quarteroni's life, I mean his life between his first steps in elementary school and his entry as an university student in the famous College Gisler in Pavia, is even more astonishing and impressive than the successful second part of his life. Alfio told me about his very personal history many years ago. Clearly, I cannot break here his life's privacy. Dear Professor Quarteroni, I would conclude my speech by expressing my best wishes to you as a new member of our academy.
Thank you very much, Professor Birauda Vega, and thank you, Mr. President. It's a great honor to be here for the first time in this fantastic place and to be part of this prestigious academy. It's really a great privilege. So today I will talk on something that has nothing to see with boats and with yachts, as you see. It's about to say using mathematical models for the heart. So first of all, let me just say that this is not a one-man achievement. I have several collaborators, and some of them are in Lausanne, the PFL, where I've been spending my last 20 years, and others are in Politecnico di Milano, and others again are somewhere else in the world, say. I presume that there are mathematicians, colleagues in the room, and people who may not be necessarily aware of the way heart works. And I apologize if they are doctors. I will just give some elementary introduction to the function of the heart, because then I will take advantage of that in order to model the heart mathematically. So heart is made by 4 chambers. There are 2 atria and 2 ventricles, and blood enters the heart through the superior vena cava, and this is the venous blood, which brings toxic substances, CO2 and other toxic substances. So it enters the right atrium, and then it passes through this valve, which is called tricuspid valve, into the right ventricle. Then it goes through this artery, which is the pulmonary artery, to the lungs, where it releases these toxic substances to the air through the respiration, and it injects oxygen. So it returns to the heart through these 4 pulmonary veins, and it goes into this atrium, and then through this valve, which is the mitral valve, into the left ventricle. And when this squeezes, then it is ejected into the aorta, and it reaches the rest of our body. So this is the basic mechanics of the functioning of the heart. Now, to have an idea of the work that the heart makes, it's useful to think that in a life cycle, our heart ejects about 1.5 million barrels of blood, and this reaches the estimated 75 trillion cells in our body. Now, what is incredible is the heart is almost empty, right? There is, yes, 4 chambers, and the part which is, say, represented by the muscle is very tiny, and yet it's capable of producing a work, an effort, which is comparable every second of our life to the effort that we need to squeeze a tennis ball. Just to give an idea of the amount of work that is made by the heart every single second of our life. Now, to understand how it works, at least from a mathematical perspective, I think we have to start from the very beginning and talk about the cells in our heart. So typically we have 2 different types of cells. The so-called non-excitable cells we have typically in our muscles. Well, when you apply a stimulus to this non-excitable cell, you have an excitation of the potential, of the electric potential V, say, and then it returns to the resting potential. So there's a peak, and then it goes back, the potential, to the resting value. On the other hand, if you have an excitable cell, like those that you have in our heart, when you have an excitation, you apply a stimulus, then you see the depolarization, which is followed by a second phase, which is the early repolarization. Then you have the red phase, which is a plateau, and then you have the repolarization. You have 4 different phases, right? So this is a very distinctive feature of the heart cells, say. Now, every second of our life, luckily, there is an electrical stimuli that is applied spontaneously in a specific place, which is the Sino atrial node. Is placed more or less here in the upper part of our right atrium. Then this reaches another node, which is called the atrioventricular node, very, very quickly, in about 120 milliseconds. Then, through this network, which is called the Purkinje fibrous network, it travels at a speed of 2 meters per second, and it reaches virtually all the cells of our myocardium. And during the plateau phase that we have seen before, the cells contract. This is a very complex mechanism that you can try to explain, and indeed you have to model at the end by equations. And this is a very, very, very schematic, synthetic explanation of a very complex process indeed. So the action potential, which is the potential that is generated by the stimuli, reaches the muscle through the Purkinje junctions. And these are the junctions in the network that we have seen before during the plateau phase, the red phase, say. Then the calcium enters in the contractile units of the cells. These are called the sarcomeres, right? The sarcomeres. Then this triggers the release of calcium from the sarcoplasmatic reticulum, and this increases the overall free calcium concentration. Now, the myofilaments that compose the sarcomeres form cross bridges, which allow to slide one over the other. And this mechanism allows this cell to relax and to contract. And now you have to think that the aggregated mechanism of relaxation and contraction of every single cell determine the relaxation and the contraction of the whole muscle. So there are two events. One is electrical, the other is mechanical, that produces the contraction of the heart and therefore allows our blood to be ejected from the ventricle. Now, to have an idea of the strange behavior of the heart, well, this is a real heart, of course, these are real images, and from a, say, physical viewpoint, we see that this behavior, this mechanical behavior, is characterized by large deformations, big deformations, and large forces that applies instantaneously due to the stimuli that occurs in a very short time, and a synchronized function of the all four chambers, as you see here. Right? Now it interacts with surrounding tissue. Heart is indeed immersed in a sac, which is called which is surrounded by the pericardium, and it contracts. And to make a very complex story very simple, you have to think of three different types of displacement. One is the shortening, is about 30%, right? Sorry, this is the sound, but it's going to disappear soon, right? So this is shortening, and then is dilation of the myocardium, and on top of that you have torsion, you have rotation. So it is because of this very strange, complex mechanism that the heart is capable of producing this type of effort. So we like to be able to reproduce all these functions mathematically. So practically speaking, this means that, well, we take the art, okay, this is the art, and we understand it, we try to understand it at best as we can, and then we put it apart, and you try to work now only on paper, right? Using paper and pencil, and then later the computer, of course. And try to reproduce all this behavior into equations, through equations, mathematical equations. So how do you proceed? Well, as very often you do in life, when you have a very complex problem to solve, to face, and you start to attack it by sub-pieces, right? And this is what we do, actually. Well, we can call this computational thinking. We try to end up with different pieces which represent specific sub-processes, and then we'll glue them together. So one is, you see this block is electric potential. So here, we try to model the stimuli and the propagation of the electric potential through all the art, and represent it into equations, through equations. This is another block which describes the ionic activity at every single cell. So this is the biophysics that occurs at the cell level. This is the mechanical activation. We want to be able to produce the stretching on the cell, the relaxation of the cell, of the myofilaments actually. This is the active and passive mechanics. This is mechanical deformation of the myocardium, of the whole heart. And we call it active and passive. Passive because every time you have a mechanical structure and you apply a force, it reacts, it deforms. This is the passive reaction. But on top of that, here you have the active action, because the active part is induced by the presence of the electrical field. So even though you do not apply any force to the heart, it will deform because of the electrical activity. This is the active component of the displacement. And then you have the fluid dynamics, because in the four chambers, you have blood. So you have a fluid that you want to represent. You want to represent the motion of this fluid. And then, of course, you can go even further, and you have the valves. We have 4 valves that we like to, again, to model. And then you want to connect this with the overall circulation. So this is the big picture, right? Now, you see also arrows here, and the arrows indicate the way these different blocks interact one another. Of course, everything is coupled together. So mathematically speaking, this is a couple problem, and of course it's a nonlinear problem because all these interactions are nonlinear, right? So this is a bit of a scaring picture. So this is only for my colleagues, mathematicians say, and I simply would like to spend 2 minutes by trying to addressing the type of equation that you have to produce or to investigate in order to solve the problem. You see the electrophysiology is a system of nonlinear reaction diffusion equations. And the solution of this system of nonlinear reaction diffusion equation, of course these are partial differential equations, is the intracellular and extracellular potential. We have two variables, and also we have this W and C variable. The C variable are the concentration of the different species, the calcium, the potassium, and the other species in the cells. And W is called the gating variable. So the cells have channels. Through these channels, you have ions passing through, right? And W is the state of the opening or closing. So it's a binary variable. W is 0 if the channels are closed. It's 1 if the channels are open. Now you have another equation, which is an ordinary differential equation, and describes the deformation of every single filament. Then you have the mechanical deformation, and you have a classical elastodynamic equation for solid mechanics, say. And of course, this is nonlinear because of the presence of both the passive and the active components. And then you have the Navier-Stokes equations for the fluid, and then you have other equations for the valve displacement. So this is at the level of the left ventricle. And then you have the same thing for the other ventricle, and for the atria, and then you have to connect it with the pulmonary circulation with the external circulation. So this is the global picture. This is the global, say, kind of monster set of partial differential equations that you have to solve if you want to provide a global picture of the simulation of the circulation. All right, but what we do in practice once you have set up this set of partial differential equations? Well, we want to solve a problem that corresponds to specific individuals. And therefore, you have to feed the model with data. So how do you get data? Well, we start from medical images, right? MRI or CT scan or digital imaging, and you have digital angiography, sorry. And you have to start from there, reconstruct shapes. The shape of a specific ventricle of a specific person, for instance. And of course, there are very many techniques to do that. This is a kind of pre-processing that you have to operate in order to provide the, the data that are necessary to solve the problem. So this is what you get. And these are just two ventricles. You have the left ventricle. You have this very thick myocardium here because it has to produce this very strong effort. And this is the right ventricle. This is the septum, and of course the atria on the top of that. And this is another element that you need in order to run your model. These are other data. You have to describe the fibers in the myocardium. So the fibers are very important because in particular they conduct the electrical stimuli. And that today is not possible, the fiber from medical images. Actually, you can get the fibers, the orientation of the fibers on the endocardium and the epicardium, which has the two external layers membrane of the myocardium. But you have to reconstruct the fibers at the interior. So you need to use mathematical methods to construct what you do not know physically. Right? And this is very critical because if you fail, you may have a completely, unphysical behavior of the heart. So this is a heart from a real person. It is contracting. These are two successive times, right? What you see here is the deformation of the heart. What you see here on the scale is the displacement. And so blue is the minimum displacement, red is the maximum displacement. So this is a time t, say, and this is a time t bar, which is larger than t. This simulation is obtained by using a certain type of fiber distribution. This one is made for the same heart, but with a different fiber distribution. And you see the way this is totally different than this deformation. So the way you reproduce the fiber is very important to get eventually results that are meaningful. So what can you do once you have this model set up? Well, you can try to simulate physiological behavior of our heart. For instance, this is the left atrium. LA is the left atrium, and this is the electric potential that propagates in a healthy heart, say. So you see this wave that is propagating with a front that is very smooth, very regular, and this is an healthy heart. This is an unhealthy heart. Actually, we are here inducing two additional stimuli in two ectopic places, and you see the way the front of propagation is perturbed. So you have these beautiful pictures, beautiful waves propagating all possible directions, but this is a kind of chaotic process, which is very much at the basis of the arrhythmia, and it could end up with fibrillation. And this is, of course, very dramatic for the patient. And this is what you get by inducing two extra stimuli on top of the one which is physiological, right? So you can use this model, for instance, to reproduce this effect. Doctors call this the A re-entry. 8 because this, you see the pattern here resembles a 8, the 8 number 8, say, this one. And so you can reproduce this mathematically and hopefully try to help the doctors for the ablation. Ablation means, roughly speaking, to use a laser and apply heat in order to burn specific points, in order to interrupt this circuit that they call a rotor, right? To interrupt this, pathological behavior. This is a very lengthy procedure. It might take 4 to 5 hours in the operating room, and it's very experimental. Doctors are extremely good, but there is not really a theory to do that. So they may ablate 10, sometimes 20 times, 20 different points, and we try to provide possible criteria, better criteria on the strategy for ablation by computing many different scenarios and see the effect. This is the mechanical deformation of the heart under the action of a ventricle, actually, under the electrical field action. So this is, these are 3 different views of the same ventricle, again, taken from a real patient. You see the way it contracts, and you see here the displacement. So it's a quite important displacement. This is an healthy heart, again, and this is an unhealthy heart where you have a necrotic region, for instance, because this patient had a stroke, right? So you have a necrotic area here, and you see the way this heart contracts and relaxes, right? And again, you can do it mathematically and try to simulate 3 different situations. One is a small necrotic area, the other one is a very large one, and the third one is a medium, right? And you want to end up with something which is important for the doctors. This curve here is called the PV loop. The PV loop is the pressure volume loop, right? This is the volume of the left ventricle on this x-axis, and this is the pressure, right? And here you have 4 different curves, which are closed curves. This is the PV loop. So the most external one, which is black, is the healthy one. So it's a heart that is pulsating in a regular way. The others correspond to small necrotic area, medium, and large. And please note the large one. So the loop is much, much smaller than the healthy loop. And indeed, if you measure the diameter, namely the distance between the 2 vertical sides, in this case, this diameter is called the stroke volume. This is the amount of volume of blood which is ejected by the ventricle. So in this case, you see that the stroke volume is much smaller than the healthy stroke volume. So this is a way to measure the efficiency of the heart, how much volume of blood can eject in a single second, say in a single heartbeat. This has to see with the fluids inside the volume, inside the 4 chambers, in particular inside the left ventricle. Now, the fluid is, again, is a blood. So blood is not really a fluid. because it's a plasma with particles, which are red blood cells, white blood cells, and platelets. So physically speaking, it's not even a fluid, but you can use the fluid assumption because in large context, in large arteries and in the ventricle, you can assume it behaves like a fluid, which is the case. So we use the Navier-Stokes equations for that. So these are the classical Navier-Stokes equations for incompressible viscous fluids, and we solve the problem. And here is an example of what you get on an healthy heart. You'll see the upper part, there is the atrium, and in the lower part, there is the ventricle. And they are separated by this valve, which is called the mitral valve. So you'll see that here is a time. You go from 0 up to 5 seconds. So we have 5 heartbeats. And you see the blood entering into the atrium through the 4 pulmonary veins. Then it wins the resistance of the valve. Here it enters into the left ventricle. And then when this contracts, this is ejected through this section, which is the aortic valve. So this is the fluid part, right? The fluid motion in an healthy heart. Again, this is the atrium, and this is the ventricle. And please note the deformation of the ventricle and the deformation of the atrium during the heartbeat. So this is the fluid on an healthy person, say. And there is a debate, scientific debate, on whether or not this fluid is turbulent. So are we turbulent? Do we have turbulent flow inside our body? And the answer is not clear yet. We believe that the fluid is not really turbulent. However, it is in transition to turbulence. It does not have enough time to fully develop the turbulence, but is constantly in the transient phase, so in an unstable phase. And you can have an idea by looking at the macro structures that are formed in a healthy heart during the heartbeat. You see these big coherent structures that are formed, and they are there to witness that the fluid is very unstable, even though not yet fully turbulent. But this requires a very ad hoc numerical methods to capture this type of potential instability. Of course, then we have to solve the problem to account for the displacement of the valves. This is the aortic valve, is a 3-leaflet valve, and this is a heartbeat. So this is the aortic root, and down there you have the upper part of the ventricle, the left ventricle. And here you see the sudden opening and closing of the 3 leaflets and the fluid dynamics around that. So we color these, say, blood particles according to the age, to their age. What is the age? This is the time that every blood particle spent in the heart, in the left ventricle. And you can see that for a healthy heart, every particle stay in the ventricle for no more than 3 heartbeats. So every 3 heartbeats, the blood is completely renewed in the ventricle. And this is also a very important consideration, because you never had the time, there's no time for these particles to to sediment or to stagnate there. So this will produce stagnation area that eventually will produce clotting, and this will be extremely critical. But this, fortunately, is not the case on an healthy heart. All right. So if I still have a few minutes, I like to now make a kind of overview and see the way the heart then is embedded into the rest of the circulation. Right. So first of all, why do we study this type of problems? Well, we study this type of problem for 2 reasons. The objective reason is that the cardiovascular diseases are unfortunately very important, and it is estimated that in Europe they regard the 45% of the deaths, natural deaths, all over the Europe. So is by far the most relevant and crucial pathology in Europe, and is about the same in United States and in Japan. This is the first objective remark, right? I mean, we are induced to study this problem because it's a very serious problem with a great impact, for instance, a great economical impact. So it is estimated that 200 billion euros are spent every year in Europe for these type of pathologies. Now, the second remark, the second motivation is more subjective, right? What can mathematicians do for that? Well, they can try to use methods that are not invasive, like those that I've been describing, and to try to simulate the physiological situation. And this is a contribution to just to the knowledge, scientific knowledge. We want to help doctors to better understand what's going on in our heart and in our body, right? Without undergoing very severe exams and going much beyond the images that are available now. And this is the very first thing. This is just contribution to the scientific development. The second one is sometimes to help doctors to better behave in terms of caring, improving the therapies, right? And thirdly, to help them in some specific surgery, operations, to better design the operations. We do it with many different hospitals. For instance, we use doctor to design better bypasses, coronary bypasses, or to work on valves when there is the transplant of valves, which is very often the case, and so on and so forth. So, of course, you're not going to replace the doctors, right? But you have the ambition to provide additional knowledge, quantitative knowledge, and to describe scenario to make forecast, which is not possible today in medicine. You can have beautiful images, but you cannot make forecast to see the way specific situation will evolve, right? Since here we're solving problems, dynamical problems, we also have the possibility to make simulation for, say, the future. Of course, whether or not these are accurate simulation and trustable simulation, this is a different story. Okay? But in principle, we have this type of possibility. So this is a very specific artery that we have in our body. This is called the carotid artery. We have two of them actually in our neck, one on the right and one on the left, and they bifurcate, and the internal branch brings blood directly to the brain. So here we see the way this artery deforms, right? You have blood inside, and the colors refer to the velocity of blood. So blue means low velocity, red means high velocity. Of course, the velocity is not uniform, it changes from one place to the other. And then you have the deformation of the vessel, because fortunately for us, our vessels are not rigid, they deform. You have elastic deformation, right? So here we're solving the coupling, the couple problem between the fluid inside and the elastic deformation. Well, this is a bit of mathematics, maybe I can skip it. So those are the equations for that. And once you have this type of solution, we can open up our mind and look at a more extended picture. For instance, this is the ascending aorta. So our heart is somewhere here. This is the ascending aorta from a real patient, an healthy patient. Those are, you see, the carotid artery, the carotid artery that I was mentioned before. And here are simulating two heartbeats. We go from 0 up to 1.8 seconds. So these are two heartbeats, right? And you see this is the first systolic peak when you have contraction and the ejection. So everything is red because the velocity is red, velocity is high. And here is a detail. You take a cross-section and you have a detail of the three-dimensional behavior of the blood, right? And this is the diastolic phase when the heart relaxes. And now there is the second heartbeat. You start again, and you have again the systolic peak, and so on and so forth. So you can go further and further and try to have a larger picture of what is going on in our circulatory system. But how can you account for the whole circulation? So just to give an idea, we have one single aorta. We have about 100 large arteries. Large in the medical terminology means with a diameter which is at least 2 millimeters or larger. Of course, the aorta has a diameter which is 3 centimeters, right at the beginning. So we have some 100 large arteries, and we have then thousands of small arteries, and we have billions of capillaries. And everything is connected, right? It's a complete network. How can you account for all those elements? Of course, you cannot use Navier-Stokes equations to solve all these pieces. This will take forever, okay? Then you have to somehow invent different approaches. And the way we proceed is this one. This is just the schematic representation. We use a three-dimensional analysis for large arteries. We use, for the peripheral capillaries, we use the analogy with the electrical circuit, and we solve all the differential equations. We want to compute the resistance, the inductance, and the capacitance. And then in the intermediate regime, we use one-dimensional flows. So you see this in the picture, right? Now, these greens are the capillaries. These are zero-dimensional circuit analysis. Then the big issue that you see here is 3D. So we start from a 3D, and then we go to the 1D. These are the major arteries and veins that we have, where we use the one-dimensional analysis. And then we go to the 0D, zero dimension, to describe the capillaries. So we connect all together these three different type of mathematical models. And again, there are equations to reproduce that. I'm not going to insist on those equations, but I'd like to make an historical remark. So the very first person, the very first scientist, as far as we know, who provided the very first model for circulation was Euler. Euler was a very famous mathematician. He has been perhaps the most prolific mathematician ever. He was blind, and nonetheless he was incredibly, strong in the analytical derivation and, of course, basic understanding of so many different difficult problems in mathematics. So Euler was studying the fluid in a tube, in a cylinder, like this bottle, say, but he wanted to consider a cylinder with elastic walls, like the ones that you use in our garden, and you have to make the irrigation in the garden, right? And our vessels have the same type of structure, so they're cylinder with an elastic wall. And Euler derived a one-dimensional model for that. It was only interested to consider the medium line here, and to derive equation for the medium line. So just to consider the velocity in the longitudinal direction. And he ended up with these famous equations that are called Euler equations that people use, for instance, in aerodynamics to design aircrafts. But indeed, the very origin of the Euler equations was for blood flow. And indeed, Euler wrote, see in the Opera Postuma, there is this paper from Euler from the 1775, right? And the title is, is in Latin, Principia pro motu sanguinis per arteria determinando. This is the original title, so you can translate it into principles to determine blood movement through the arteries. So, these are the original Euler formulae. Of course, this is not in the form that we are using today, but the meaning is absolutely the same. And what is surprising or astonishing is this phrase by Euler. So Euler had this discovery, and he sent his paper to the Academy of Dijon in France, right? Because there was a prize, and this was the prize of these were 30 louis d'or, and this prize was paid by the French Academy of Sciences at that time. So he sent this to Dijon, and then he said, this is Euler, last March I sent a piece on the motion of fluids in elastic tubes to the Academy of Sciences in Dijon, which had set a price of 30 louis d'or on this subject. And then, this is the commentator, having received no answer, Euler feared that his entry for the Paris Prize, this was called the Paris Prize, had been held up or lost. And this is the remark of Euler, which I very much regret for this reason only, that I've kept no copies of these pieces. So he was afraid that his work was lost forever because he didn't make any zero copy of that, right? It was impossible at that time to do that. And what is even more important is the very last sentence of his paper. So he concluded his paper with a very pessimistic philosophical statement. He said, since there appears to be no way in which this can be completely resolved, because there is no way to find an exact solution by paper and pencil on these other equations, yeah, this investigation can be considered to transcend human powers. The work will end here. So, of course, he could not imagine at that time that centuries later there would have been numerical approximation and more than that, computers capable of addressing this type of difficulties. So, this is the reason why Euler is considered to be the father of the hemodynamics, at least in the mathematical perspective. Now, you can use the Euler equations and to derive the one-dimensional model for the arteries, and these are the most important arteries in our body. There are 104 in this specific case, and you see you can reproduce a behavior in, like this one, You see, this is the set of one-dimensional arteries. I can describe the one-dimensional flow motion in the artery. These values are the values of the pressure. And then what we do, we can connect these with three-dimensional models in those pieces where you want to have a much better investigation, and of course in the heart. So that's the way we can make the patchwork between zero-dimensional, one-dimensional, and three-dimensional in order to have a complete picture of the heart. And this is just a detail on the way we couple 1D model with 3D model of the heart. All right, I'm going to conclude by mentioning a very difficult and challenging problem. Is this going to be really useful for medical doctors? Well, I think we have to make a remark. If we talk in terms of basic understanding, I would say definitely yes, right? For some of the reasons that I was mentioning before. But this is in the realm of the academies, in the university. So its scientific work is certainly valuable, right? But is it going to be actually used in the clinical practice, in the daily practice? Now here, the main factor is time. How long does it take to solve those equations that we've seen before? Just to give you an idea, to have a single heartbeat, which is 1 second of physical time, it takes order of 1 week on the biggest European supercomputer. Because our life is so complex that if you want to capture all the tiny details, you really need to spend all this time. Of course, you cannot pretend going to a doctor and say, okay, let me try to make a simulation for your patient and come back in one week, right, for a single heartbeat. This has no sense. It, again, is valuable from a scientific viewpoint, but not for the daily practice. So the idea is to try to bring all this to a reasonable level where you can solve those problems in a very quick time, ideally real time. So what is real time? Well, real time depends on your counterpart. Real time for me is the time that you have in order to not lose the patient of your medical doctor, right? So it's a short time, say order of minutes, maybe, certainly not of hours, right? So can you bring all this to the level of 1 minute computation? And this is a big challenge. This is where you are working on these days, and this is the idea. So it's kind of very complex method, but I try to convey the essential idea. So assume that you have several patients that for a natural reason, spontaneous reason, they go to hospital and they are monitored and you have data, so you can simulate their heart behavior for each of them, 10, 20. Assume that you have a database worldwide, 100, 1,000 from different hospitals, right? Now, to make the numerical simulation, this can take for 1 week, 1 month, 1 year, it does not matter. This is your investment, right? You are investing in knowledge. So you use the biggest supercomputers to produce, see the behavior of the heart of this specific person, of this specific person, of that specific person, and so on and so forth. And then this is your database, right? Having all these solutions, pre-computed solutions. And then you have a new patient coming, which is different than anyone else, right? And you want to end up with a very quick solution for this patient. So what can you do? One possibility is to solve this big problem for this patient by using this pre-computed solution as basis functions. This is a mathematical terminology, right? So we want to see this patient, the solution to this patient, as being a linear combination of the solution of all those patients. So if you have 100 patients, this will end up with a problem which is 100 by 100. that you can solve in real time. Whereas to solve this problem, you may use 10 million points, finite element points, and this is why you are taking so long. So you are basically, this again is a mathematical statement, you are basically projecting all the individuals, the solution corresponding to all these individuals, in a subspace of very small dimension. And then when you have a new patient, you want to look for a solution in this reduced space, say. That's the idea. So we want to account for the diversity, we are all different one another, right? By setting up mathematical methods that are capable of capturing this diversity and introducing it into very quick feedback. And this is the way we believe we can attract and keep the interest of the medical doctors. So we already have some experience on that, but this is a big issue, and we are proceeding in this way. All right. I think we'll stop here, and I'd like to thank you very much for your kind attention.
I'm just having here the privilege to ask you, Alfio, that probably the first time we met was in Pavia, maybe in 1980. And that time, you were probably, as I was at that time, not taking mathematics to the heart, but the heart to mathematics. So we were starting as a PhD or postdocs in mathematics, and that was not only our brain, but it's also our heart. So in that sense, this is a very interesting occasion, and my question is exactly, now that you have also taken mathematics to heart, how do your heart feel about these advanced in applying and developing mathematical methods that were very, very, very important to our heart during our careers, to now to this fantastic presentation that you are achieving now?
I think this is a very good point of view and very good remark. Well, I try to give two different answers. One is more or less serious, and the other one is not that serious, if you allow me. So the one serious is that I've been working on different type of subjects, but while working on medical model for medicine, mathematical model for medicine, has a special value because, of course, is a challenge. But if you end up with something nice and useful, you know that in principle you are going to serve a very large community, not only the one of mathematicians. This is, of course, a very ambitious project, but this gives a very special, how to say, energy to our art in order to address this type of problem. So it's a very unique opportunity for me to work on problems with a broader spectrum of interest, say. The second remark I'd like to make is that I hope that my own heart will resist in these 4 or 5 years, because after saying that we're going to use mathematics to cure heart, I don't want to be the counterexample, right? This would be tragic. So I have a special reason for not getting sick, or at least, you see, having a very serious sickness for the heart, because I feel this responsibility.
Okay. Thank you very much. Now, with the permission of the President of the Academy, okay, maybe you can also, as a patronage lecture, to ask people if they want to put some questions. Yes, and if you want to ask, maybe for register is better.
Do you mind if I ask a question? I was absolutely charmed by your lecture, Alfio. I am an economist, and I would like to remind you of what Keynes said. It's better to be approximately right than completely wrong. So with that in mind, and with the use of Euler equations in our field, I was really wondering, before you had that last slide, when would you be able to actually map an actual heart of an individual? And then you had this reduced order. And that is very hopeful, as you said very rightly. But again, I mean, when you come to medicine, to particular conditions, it is the individual that matters. So I wonder if this linear combination, I mean, it's a tough question, I'm sorry. Imagine, you know, you are, is that enough? So the method is fine for approximately right, which is better than completely wrong. But is it enough, is my question.
Great question. Okay. I have potentially a very long answer. I try to contract it as much as I can. Mathematicians call and engineers call this type of consideration the validation. So you have a model, how do you validate it against the reality, right? So how do you validate these mathematical models in a medical environment? Very difficult, extremely difficult. Of course, we are talking about individuals who react in a different way. Not only different individuals react differently, but also the same individual over time, in 1 hour, you repeat the measures and you see a different type of behavior. Okay, so the very first answer is that there is no way in this field to guarantee or to certify the exactness of your model and of your answer. If I had to certify the answer, the simulation of the way this fluid behaves in this bottle under this solicitation, I think we are able today to provide an answer which is accurate to 1%, 1 per 1,000, 1 per 10,000, is completely under our control, right? The same for an airfoil, for a wing, for an airplane, and so on and so forth. But here we're talking about human being. So what is actually the role of the model? The role of the model is never to provide an answer which is accurate in this specific case. We're not going to say that in this specific part of the heart, the stress is equal to this up to 3 significant digits. This is totally wrong. What do we do with doctors? We describe trends. For instance, assume that you have to put a bypass to a new individual, or a newborn baby who has very severe pathological malfunction, right? So you have protocols, and you have 2 or 3 or 4 different type of protocols to use for that specific case. And the doctors decide on the basis of their art, of their knowledge, of their statistics, right? Of their intuition. So here you can try the 3 different protocols before and see the way the blood redistributes. And you can say, I'm not going to certify the exactness of the answer, but I can tell you that this is better than this on that. On the other side, if we're talking about order of 10% of error, I cannot say that we can guarantee 10% of error, but you are in this type of regime, I would say. So you have to be aware of what is the potential and what is the intrinsic weakness. But we certainly enlarge the possibility of providing answers that are useful.
Yeah, there'll be another one over there.
Thank you very much for your talk. I had a question about the model equations that you showed in the third slide. You explained that the heart was divided in subdomains, and you have different kinds of physics. Then you have 6 systems of PDEs. You didn't mention the boundary conditions. I guess it's a difficult problem, and it is an important task that you had to achieve. And related to the last question, maybe because the boundary condition inside the heart and with the rest of the body also, between the heart and the rest of the body. And as related to the question that was raised now, is this kind of model for biology not an example of data-driven PDEs, data-driven models? Because
you say data-driven?
Data-driven, because you need, of course, to validate it.
So the first remark is that I did not talk about boundary conditions, but basically we have 2 different kinds of boundary conditions. One is the way, what is the boundary of the heart? Right? The external boundary is with the pericardium. Okay? This is the first boundary condition for the mechanical behavior. And there we have, in principle, you should simulate the interaction with external organs, which could be bones or muscular tissues or other things. We do it with a spring model. by changing the elastic behavior in the external boundary, accounting for the stiffness of the external tissue. So this is a kind of Robin nonlinear boundary condition for the external pericardium, say. Then the heart is connected to the circulation. And if you see the heart by itself, the boundary should be, for instance, the aortic root, right? This is one way. You can prescribe the velocity profile on the aortic root. But we do not do that. We connect it with external circulation. So the system is a closed system. And this is precisely a way to avoid enforcing boundary conditions that are not physiologically correct, because this will produce some backflow which is not physical. Now, data-driven, yes, of course. For every model you have data, the model, which is based on general principle, and the solution, right? 3 blocks. Data, model, solution. Data here are the shape of the specific individuals, so the artery or the ventricle or the whole heart, and other data, like the distribution of the fibers, like the conducibility, electrical conducibility of the tissue, if it is scar tissue, if it is an infarcted tissue, or it's an healthy tissue, for instance, and the blood viscosity, blood density, and so on and so forth. Very often we do not dispose of all this data, because this will require very invasive intervention, right, on patients. So we try to recover this data through techniques that are called either Kalman filters or data assimilation, mathematical techniques. So we compare with measurements, and we try to take advantage of that by Kalman filters of data assimilation in order to recover the values of those parameters or those coefficients that are not given.
Possible to simulate hearts where you have certain percentages of necrosis in the myocardium, so that you can predict how the heart will behave with 1, 2, 3, 4% of necrosis, because that would be very interesting, and it might be possible to correlate this with clinical cases.
Actually, this was one of the simulations. In this case, we are simulating a large necrotic area, and small one, and a medium one. So we are assuming that part of this ventricle is interested by necrotic field. This one, and this one. And you see the way the heart reacts, and you see this picture that tells you the capacity of the heart to eject a specific volume of fluid. So these are simulation description of scenarios that, again, can provide some information to the doctors. And you see the way the heart deforms is totally different, right? You see the actual form of the heart at the same time is different, of the ventricle. Yeah.
Sorry for not having simulated the moment.
No, that's fine. I mean, I've been talking about very many things, but your question is absolutely pertinent.
Any further questions over there? Yes, please.
Hello, just a short question. So inside the heart you have 3D Navier-Stokes equations, and if I understood correctly, at far away in the arms, you showed that you are modeling this with electric circuits.
In the peripheral.
Yes, those are 1D equations. How do you put together 3D models with 1D?
Of course, I've been hiding all the mathematical intricacies, right? This is a very general question indeed. How do you connect 3D with 1D? You may have a lake with a river, and you'd have the same problem, right? You have 3D and then 1D, right? We base this derivation on an asymptotic analysis. So we reduce the 1D. The 1D is indeed a 3D. Right? So we reduce it asymptotically, or asymptotically, and as part of this process, we recover the interface conditions. And typically the interface between 3D and 1D, or 0D, we enforce the continuity of, the conservation of mass and the conservation of linear momentum. Of course, this takes different form in 3D and in 1D, but this is the guiding principle. You don't want to have leakage, which would be a numerical leakage, right? And you don't want to, so you don't want to lose mass, and you don't want to lose the equilibration of stresses. So this is the principle.
Any further questions? No, if not, I would like to thank Professor Alfio Quarteroni. It's very interesting. As an electrical engineer, I have been simulating physical systems all the time. But they are physical systems, not living tissue. More recently, I have seen quite a lot of simulation of living tissues, but muscles. Today, I saw for the first time muscles and blood, which is definitely a far more complex situation. So it was really fascinating, your presentation. Thank you very much indeed.
Thank you.
And I'd like to present to you the symbol of being a member of our academy. It is inside.
Great honor.
It is the diploma. That tells you your name. Yes. Everything is right.
In principle,
Should be in Latin, of course.
this is really serious.